Begin the fire and explosives unit by talking a little bit about the chemistry of fire. And while we don't need to be super experts at the chemistry, you need to have some idea of what's going on. All right, so what is a chemical reaction? So chemical reactions involve substances breaking apart, breaking chemical bonds, which releases energy, and making chemical bonds, which absorbs free energy, and is the overall releasing and absorbing energy. If I sum total all the bonds being made and all the bonds being broken, at the end of the chemical reaction, I might overall release energy, or I might overall gain energy. And so that is the overall reaction energy. We also have something called an activation energy. Even if I have a chemical reaction that in the end, when I'm done, gives off more energy than it takes, the initial making of bonds might take some energy. I might have to do some prep steps. You could consider this like a startup cost of doing business. So maybe you have a reaction that will give off energy, but it's going to take some energy to get started, and I need to fund it with that. And in fact, we see that with fires, right? Fires give off a lot of energy, but they don't start by themselves. We need to kickstart them with some heat and some energy in different forms. So we talk about the energy form that we're going to use to supply this is generally heat. It could be other things. It could be lightning. It could be electricity. It could be light itself. There's a lot of different forms of energy, but we're typically going to use heat. So exothermic would be a process, a chemical reaction that releases heat energy. Fires are exothermic. Endothermic is a process that absorbs heat energy. Other common forms of energy are, like I said, that light and electricity, and we see those as other forms, but since we're talking about fires, we won't worry about that too much. However, understand that the expanding of gases, right? There's gases made in a fire. We make smoke. And those gases, when they expand outward, actually is another form of energy, right? That's explosions, right? We're going to take that energy and we're going to make it into an expansion of gases that can do a lot of work. So sometimes we want to show a chemical reaction as a before-after picture in terms of its energy. And we tend to use these energy profiles. So on the left-hand side, we have reactants, and this line suggests that since energy is increasing on the axis, that these reactants are at lower energy than the products. And then as the reaction happens, so we're going from reactants to products. This is suggesting that it has to go through a stage where I need a lot of energy. I have to get up to this energy before I can get down to products. The distance between the reactants and the highest point in the middle is the activation energy. So this does have an activation energy. However, when I'm done, notice the products have more energy than the reactants. So this has to absorb energy to get up there. So this would be an endothermic reaction. Over on the right-hand side, we have a different one. Here we have reactants and then I have products at a lower level. So the products have less energy than the reactants, meaning when I'm done, I will have given off energy. This also has an activation energy involved in it. Sometimes we can have something that we add to a system called a catalyst that lowers that energy and makes it more likely that this reaction will happen. So we will see that in sometimes. So here we have our activation energy in our products. Again, this general idea of how to look at a profile and determine whether something's endothermic or exothermic, and if there's an activation energy to it, that's what we would get out of these energy profiles. A couple of key reactions that we might see. One is an oxidation reaction. Typically reacting with oxygen, there can be other oxidizers, not just oxygen. So rusting is an example of a oxidation reaction. Iron rusts when it's in the air, so the oxygen in air can create rust. Also, our fires are typically combustion. So the fuel in a gas engine, also the wood in a structure fire is a hydrocarbon, and when we react it with oxygen, it makes carbon dioxide and water, usually both in gas form, so it's like smoke. So that combustion it's a type of oxidation reaction, and it is generally going to be spoken of as some fuel plus oxygen makes carbon dioxide and water. They're almost all exclusively exothermic. They're going to release energy as heat and the light in the flame. And that released energy sometimes serves as an activation energy for another fire to start. So the heat from one fire can be the activation energy to start another chemical reaction. Often they're gas generating. So we have these reactions, and combustion is one of them, that creates gases that applies pressure to the container. If a lot of gas is created quickly, that pressure, that pushing on the walls of the container can be so severe that it bursts the container, hence an explosion. So if a reaction is also thermic, you may also have an explosion with a fire. So we're going to see all these kinds of things in this chapter. A couple of combustion facts and vocabulary terms. We have something called an ignition temperature. This is the minimum temperature needed to spontaneously ignite the fuel. So this is kind of related to its activation energy. It's not going to happen at any old temperature, so there's an ignition temperature. Then we talk about the heat of combustion. This is how much energy is released when a substance burned. And not all substances, so some substances have higher heats of combustion. They get off more energy than others. Once the combustion starts, and there's enough energy in the form of heat and light, we begin a chain reaction. Again, that energy released is a activation energy for more reactions, and so it keeps setting off more and more, and that's that chain reaction, and we start to see the fire gets out of control. Generally, we talk about fire in terms of a fire triangle. There are three things that we need. We need the fuel. That's the thing that's going to be doing the combustion. We need the oxygen. That's also another reactant. So those two things are the things that are going to react. I need heat as my activation energy. Sufficient heat to initiate the reaction and then sustain it. So fuel, oxygen, and heat. And generally our fuel is going to be wood or accelerants, gasoline, or wax, some sort of product like that. The physical state of the fuel will affect how likely it is to react. So flame is going to be produced if I have a sufficient reaction rate. And for a flame to be produced, I generally have to have my fuel in a gas state. As that temperature of that liquid increases, it's going to start to evaporate more, right? Cold water only evaporates a little bit. Hot water evaporates much more quickly. Same thing with fuels. A liquid fuel like gasoline, as we warm it up, more and more of it's going to evaporate and be in a gas state and be capable of producing these flames. So we have the ignition temperature, but another important thing is called the flash point. It's the lowest temperature at which a liquid produces enough vapor to create this flame. So they're not the same thing. A solid, such as wood, can't burn on its own. It has to have enough heat so that it can pyrolyze. Remember we talked about pyrolysis with the paints? We talked about pyrolysis, GC. When you heat something at a dry heat to a very high temperature, it turns into gas. It goes straight from solid to gas. And so that's what we need to do. We need to pyrolyze the solid until it can then be in gas form, and then it can burn. And then we have, when we have glowing combustion or smoldering is right at that fuel-air interface. And so we'll see that, you don't see the flames happening in the middle of the fuel. You see it right where the fuel is hitting the air, and that's where this combustion reaction is taking place. We have three different ways that the heat can transfer. And this becomes important. One, I need heat to transfer to the reaction to initially start it going, that activation energy. Also, once I create this, it's going to give off heat energy. So how is that heat going to move around to other objects and maybe start other fires? We have conduction, and conduction is the movement of heat through a solid object. So if you have things that are touching each other that are solids, as one hot object is next to another hot object, it can create a heat transfer. And not all objects transfer heat well. So some are good conductors, like metals, right? They transfer heat very nicely. And other ones like rubbers and plastics are not particularly good. They won't tend to transfer the heat. Radiation is another type of transfer. And this is it's technically using infrared radiation, but essentially the objects no longer need to be touching, but a hot object emits this infrared, and it can now that light, it's a form of light that it transfers to another object and can heat that other object up. So infrared radiation is generally how, a lot of the warming happens. So if you're near a fire but not touching the fire, it's infrared radiation that's occurring. Or the sun is solar radiation hitting our bodies and warming us up. And convection is the third. And convection is about air currents. The idea is that as I move molecules in a liquid or usually in a gas, they can move heat from one area to another. Generally, as the air warms up, it rises because it's less dense, and at that point, that makes it start to move aside, and then it tends to fall back down as it cools off, and then that starts these currents. And those currents now, convection currents, can move heat from one area to another. That's kind of the basis of weather. So we have 3 different mechanisms by which we can transfer heat.